Good morning, everyone. Thank you for attending this session, where we are going to talk about how we are bringing Google's Colossus file system to PyTorch. And for anyone who is not aware of Google's Colossus, it's the same infrastructure that powers the loud apps like YouTube, Google Search, and Google Photos. Myself, Trinadh, I'm a senior product manager in Google Cloud Storage, joined by Ankita Luthra. She's a senior software engineer in Google Cloud Storage. It's incredible to see the amount of innovation that is happening in PyTorch. And as your models evolve to support various business challenges and multimodalities, they're paying a tax, a hidden tax called storage tax. What's happening is, let me explain that storage tax with a specific example. Let me take Llama 4 Scout, which is 17 billion active parameters, even though it's like 109 billion parameters and mixture of experts model. It's trained on 40 trillion tokens, which is 3 times the training tokens for Llama 3.3, 70 billion. So your training data size is increasing, almost multiplying. And if you consider 12 bytes per parameter, the checkpoint size can go up to 1.4 terabytes. Even though it's 17 billion active parameters, the total number of parameters are like 109 billion. So their checkpoint size can be 1.4 terabytes. And with the GPU cluster reliability, you might want to save the checkpoint as frequently as 5 minutes. So you need to store a checkpoint of 1.4 terabyte size in 5 minutes. And it supports a context length of 10 million tokens, which is great because now you can put in your entire repo and then get your answers. But that also means that the KV cache can run into terabytes. And you wanted to store the KV cache into remote storage mechanism like an object storage because the clusters cannot hold 1.4 or like the terabyte size of a KV cache in its cluster size, and you wanted to store it to object storage and you wanted to retrieve it, which means your latency should be very optimized in order to serve the KV cache from remote storage, object storage mechanism to your GPU clusters. So you have 2 things that you need to solve simultaneously. One, the massive throughput, because you wanted to run things at scale, and you wanted to get data faster. So that is where we are, So that's where we are excited to talk about rapid storage, which solves this exact same problem, where it is able to support 15 TIBS of speed. Please note it's a capital B. And it is able to support 20 million QPS at sub-millisecond latency. And it is able to support sub-millisecond latency for random reads. If anybody of you worked on the storage systems, you understand optimizing the random reads is a very hard problem. So it's able to support a sub-millisecond latency for random reads and up and writes. And it's the storage system that is optimized for your AML workload. And when we thought about how do we bring this innovation, fsspec was the obvious choice because it is the Pythonic file interface that is supported by the many frameworks that you are already using, be it data training or checkpointing or inference. And it supports various file system implementations, including the GCS, the Google Cloud Storage one, GCSFS. So by integrating rapid storage into GCSFS, we observed a 4.8x improvement in both random reads and sequential reads. And then we are able to observe 2.8x faster writes with rapid storage integration into GCSFS. And to talk about how we are able to achieve, I'm going to hand it out to Ankita.
Thanks, Trinadh. So I'm going to talk about how Rapid is able to achieve such a high performance. The core system which is driving this whole performance is Google Colossus. Colossus is the same system on which GCS stores all of its data, including the services like YouTube, Drive, etc. How Google Colossus is able to maintain such a high speed at such a massive level is due to its sophisticated architecture as well as its optimization techniques. Some of those techniques include distributed metadata. So the metadata, just like data, is also distributed across server in Colossus. The storage is also intelligent inside Colossus. We use ML-based algorithms to identify the usage patterns and place the data according to those usage patterns. Colossus also uses stateful protocol instead of HTTP stateless protocol, which is much higher performance than usual, giving that performance to our reads and writes. Now we are bringing all those Colossus APIs directly to GCS in the form of rapid buckets or rapid storage. So let's take a step back and see how the data is traveling between your GPUs and the storage. So we load tensors or write tensors using PyTorch from GPUs, and PyTorch internally uses fsspec. fsspec is a popular Python library which is used to expose cloud storage systems as local file systems. GCSFS is an implementation of fsspec, and it is used to talk to Google Cloud Storage in PyTorch. So how we optimized this entire communication? We use direct connectivity in rapid storage. Direct connectivity means we don't need any front-end proxy between fsspec and Google Cloud Storage. The protocol is also now stateful and gRPC based instead of HTTP based, and it is much faster. The data is also co-located in the same zone as your compute, so the network latency between data and the compute is also reduced using rapid buckets. We have also optimized the on-disk format on the rapid buckets, which means now the appends are native and more easier to do in the cloud storage buckets. Rapid buckets also support hierarchical namespaces, which means folder is now a first-class resource inside rapid buckets. That means the data layout inside the rapid buckets is more closer to local file system. So to bring all of these features and high performance of read and writes to PyTorch, we have integrated these things directly into GCSFS. Now what this GCSFS integration includes is, GCSFS now supports Google supported SDKs for rapid and HNS buckets. We also introduced stateful read handles, which means once a connection is established between your GPUs, between the PyTorch and the cloud storage, we can use the subsequent calls, and we can use the metadata from the subsequent call. We can use the metadata, and the subsequent calls can actually use that metadata, making the writes and reads much faster, especially the random writes. This would help improve your training time by quite a lot. We also introduced bucket type auto detection. So now what type of bucket you're using, whether it is rapid or it is standard, is automatically detected inside GCSFS. All the folder APIs are also now supported, as including and especially atomic rename folders, which will help reduce the checkpointing time. The appends are now native to GCS. So what does that essentially mean is, till now appends were either not supported, or to append we have to download the complete object, add the data and upload the complete object again. But now with rapid buckets, the appends are automatically supported in the buckets, and you can directly add the data directly to object in the storage. To add all these features into the GCS, we contributed to open source repository of GCSFS. We contributed almost 30K lines to add all these features. A huge shout out to Martin, who is the main maintainer for fsspec from Anaconda, and he has been very helpful and collaborative with us during this whole effort. You can check out all the features, including all the benchmarks comparing standard bucket as well as rapid bucket on the GitHub repository. The numbers are there, the documentation, all the features are added in the open source repository. So as a PyTorch developer, what changes you would have to do in your code to get all these features and to give your GPUs more efficiency? And the answer is no changes. So the rapid buckets are integrated, all the heavy lifting for the rapid buckets is done inside GCSFS and our SDKs. So you don't need to make any code changes, just create a bucket which is of type rapid, add the data in this bucket and point your workload to use these buckets. Your data access will be much faster, and your GPUs can be used, and your GPUs can be used more efficiently. They can use that save time in processing. And that's it from us. Please use the rapid buckets and give your GPUs a performance boost. If you have any questions or any discussions you want to do, we'll be available at the Google booth as well. Thank you so much.